Hello everyone. So today we are going to discuss about how to design beams as well as one-way slab if it is fixed. Okay, so far all the discussions we have done, we have assumed that the beams are simply supported. That means there is the moment distribution is something like this. There is zero moment at the near the support and maximum moment at the midspan. But in reality, if you see everywhere, you will not find means you will find, but in most of the slab beams frame or systems, or in case of normal regular structures, you will see that the slabs are monolithically casted with the beams, and you will not find that it is simply supported, except for suppose bridges and all. But in case of a normal building and all, you can see that beams are monolithically clustered with the column. So there is nothing like simply supported beams in case of regular structures. So today we will see that if there is fixed support and to the beam. Okay, in that case, what happens if there is a fixed support in case of a beam? The moment is basically something like this, right? So hogging moment at the support and sagging moment at the midspan. Now, as there is hogging moment and a sagging moment are there, so how to find out the reinforcement? You already know. Reinforcement is already know, because you know you can find out the, you just need to find out the moment and you can find out the reinforcement. That is not that big deal. But the problem is how to find out the fixed end moments. How much moment will be here, how much moment will be here. That is the main question for us. So there is in structural analysis, probably you have studied how to or analyzed fixed beams. But in case of if that is not done, so if you are not doing the or if you are not calculating the moment as per the equations that you have studied in structural analysis, so there are some other means the simple method is given in IS code, and that can also be followed. So we will be following the IS codal provisions for calculating the fixed end moments. Okay, and remember that it is similar as I have already discussed with you for one-way slab design. So one-way slab design is basically similar with that of design of beams. So here this problem will be designing a slab one-way slab basically, which is fixed all around, and it will be similar to that of a beams. Okay, so as I have discussing a slab, so the process is exactly similar to the beams. Okay, to finding out the moment and the calculation of the reinforcement. But other than that, after calculating the reinforcement, how to provide that, what are the means, how to do the detailing, how to calculate the stirrups, everything are individually you have to take care of. Okay, means slab, in case of slab and in case of beams, the only difference comes with how to detail, how to give the reinforcement, and how to give the stirrup. This kind of differences you will find. But other than that, I'm only taking this class to show you how to calculate the moment. So as far as the moment calculation is concerned, if you're designing a one-way slab or a designing a fixed one-way slab or a beam which are fixed, the process is similar. Okay, so let's take the problem here. So here it is like that. The plan of the floor slab system covering an area of 8 meter by 14.5 meter clear span is shown. So let's see the figure. Yeah, so this is the figure where we have the 8 meter along this side and 14.5 meter along the other side. Okay, and the slab raised on a 230 thick masonry wall. So here this is the wall and this is the wall. This slab supports at the end with the masonry walls of 230 thick. And for economy, the span of the slab is reduced by providing three intermediate beams along 8 meter direction. So basically what happens is you can see that the slab is very big. It is with this side one wall and other side another wall. Okay, only two support, which is a 8 meter by 14.5. It is a very huge or pretty big slab. So in the if you design this slab without considering anything, you will find that the deflection will be very large. So you have to your depth of the slab needed to take care of that deflection will be become very high. In that case, it will be very uneconomical because more amount of concrete, more amount of reinforcement will be required. But you can reduce the deflection by providing basically the some secondary beams. Some beams you can provide, and these beams, what will do, it will do, it will just divide the slab into small parts, and that's how it will. And then what will happen, it will reduce the deflection. The deflection will be now restricted over here. Okay, it will just reduce the deflection. Initially, if the beams are not there, the deflection will be as a whole, the deflection will be very large. Now as beams are provided, deflections you can restrict the deflection of the beam. So that is why it is said in the question that for economy the span of the slab is reduced by providing three intermediate beams along 8-meter direction. So along 8-meter direction we have one beam, two and three beams are there. The specified floor loading consists of live load of 4 kN per meter square and dead load of 1.5 kN per meter square in addition to the self-weight. Assuming Fe415 M25 grade of steel and concrete respectively for this another slab, assuming moderate exposure condition. Okay. Now let's see the design. So I think this figure is pretty much clear. Okay. Now the beam sizes, those are given in the drawing itself. It is 300 mm beam size is given. See here, 300 mm. So beam size is 300 mm, and slab panel, the solder length. If I want to find out the solder length, which is represented by Lx over here. So what will be the span? Which is you can see the clear span from here to here. It is 14.5 meters minus the dimension, the width of the slab of beams, that is 300 by 1 2 3 4 4 slabs are there, so by 4. So that's how you can calculate basically the width of the shortest side, which is around 3.4 meter, and the longer side is basically 8 meter. You can see the figure here. So this is from here, from the side of the beam to the side. This is the clear span, 3.4 meter, and obviously the length is 8 meter. And you can see, if you find out the ratio, 3.4 by, sorry, if I do it 8 by 3.4, the longer side by shorter side, basically obviously it will be greater than 2. Okay, so it is obviously as a one-way slab, so we can design it as a what, one-way slab. Okay, or you can just take a small strip over here. You take a small strip along the shorter side, so this strip we will take and we will design this strip, and whatever reinforcement will be required, that will provide all along, and all the spans are similar, so we can provide the same reinforcement. But here you can see that as these beams are provided, so it will just act like a support, just like a continuous beam. Remember, continuous beam, so it is just like this continuous beam. So here, if you find out the reinforcement, it is, or sorry, moment, the moments are like this. So fixed end moments are here. You will find fixed end moment or hugging moment over here, sagging moment, sagging moment, sagging moment over here. So this kind of bending moment diagram you will observe. So we will try to find out what is these hugging moments from the IS positions. So for this, we will take a complete strip along this direction. So why, if someone asks you why, because we have divided, so this is the shorter span of the slab. There is 1 2 3 4 slabs are there, and these are one-way slabs, and the shorter side of each slab is 3.4 meter along this side. So the deflection is going to be on this side, as this is a one-way slab. So that is why we have taken the strip along this side, not the other side. So the yeah, and support which is already assumed, that is 230 mm already given. Then check the type of the slab. Just now I have shown you that Ly, we have assigned this is a longer beam and this is a shorter beam. So that is 8 by 3.4 and it comes up to 2.353, which is more than 2, so it's a one-way slab and it's a continuous slab. Okay, now we will go for the effective depth. Now how to calculate the effective depth? So here you can see that if you see the strip, now I'll be taking only the strip. So this is simply supported because it is just resting over the wall. Okay, so at the end, but the both end, it is in the question is mentioned that is rest over the wall, and the other we have beams, 3 beams. So these are basically fixed. These are fixed. These are fixed, but these are simply supported, right? Simply supported. So for simply supported, the length to depth ratio is basically taken as 20, and for continuous it is 26. So it is a mixture of both. You can see this is continuous as well as in the outermost, and these are free or simply supported. So what we can do, we can take the average of these two. So that is why we have taken the Lx by 1.25, because in slab I have mentioned that approximately 1.25 we can take, we can increase, and the value that we have taken is 20 plus 26 by 2, because it's a combination of both. If it says that this is fixed, then no issue, just take 26. Okay, if this is said that this is, then it is fixed. But if you are designing a beam, in that case this will not be there. Okay, in beam it is not be there. This is directly you can take 20 plus 26 by 2 only if the ends are simply supported. If ends are also not simply supported, suppose these are fixed, this side is fixed and also it is a continuous, in that case 20 is also not needed, only 26 is there. Okay, understood? So you have to understand this concept. So this 20 is only because it is mentioned that at the end it is simply supported over some walls. So that is why 20 is there. 20 plus 26 by 2, and 1.25 is because of slab. It is a, if the question is a beam, then this will not be there. Understood? Now Lx, why Lx we have taken? Because we know that it is going to deflect in the shorter side. So that is why I am taking the shorter side itself. Okay, so Lx by this one, so it is 1 point, so it is 118.261 mm. Okay, so only we are taking the this, if other I can show you in the figure. Lx is this one, 3.4 meter is Lx, whereas the deflection will be along this side. So that is why everything will be calculating along this side. So 1 meter strip I have taken, this 1 meter strip. So we'll find out what is the effective depth, what is the effective length, and then we will find out the moment, and we'll find out the reinforcement. Clear? Now let's see. Now approximately we got the effective depth as 118.261 mm. Okay, this is what we have got. Then what is the effective overall depth approx we can take? So assuming effective cover of 40 mm, 118 plus 40, it is around 0.158 meter. Okay, so let us assume 160 mm. Okay, thickness is just an assumption. Overall thickness of the slab. The effective depth we can take it as 160 minus 30 mm as clear cover, and 10 mm for the dimension of the stirrup. So basically we'll come up with 120 mm as effective depth. Okay, now effective length we will see. So Lx by 12 is 283. Okay, so before that let's see the clauses that we have discussed for effective span. So initially we have already discussed what is for simply supported slab or beam, so it is already we have done. But what is about the continuous beam and slab? So in case of that, the continuous beam or slab, if the width of the support is less than 1/12 of the clear span, if the width of the slab, that is width of the support, is here 230, if 230 mm is less than 1/12 of the clear span, 1/12 is of the clear span, what is the clear span? Lx by 12, so it is 283. You can see that W support is less than 283, right? It is less than 1/12 of the clear span. The effective span shall be as in 22.21a. That means as per simply supported beam you can use. But if the support is wider than 1/12, if the support is basically suppose 300 mm, if there is 300 mm, then you you may not have been able to use this particular clause, that is 22.2a, simply supported beams clause. You will not be using, you will be using the following clauses. So if the support we are wider than 1/12 of the clear span or 600 mm, whichever is less, the effective span shall be taken as under, which are for inspan with one end fixed and other end continuous, or for intermediate span the effective span shall be the clear span between the supports. For inspan with one end free and other end continuous, the effective spans will be equal to the clear span plus half the effective depth of the beam or the slab, or less the span plus the half the width of the discontinuous support, whichever is less. And in case of a span with roller or rocket bearing, the effective span shall be always the distance between the centers of the bearing. Okay, so I think this is very clear from the statement itself. So if it is mentioned that if one end is fixed and other end is continuous, in that case we will be taking the effective span shall be taken as clear span between the support. Okay, and clear span or effective span already you know. And if the end span with one end is free, and other end is continuous, suppose something like this, this is overhang, suppose. In that case here what you will do, the clear span plus the effective depth, you will do the whatever the clear span you have, then plus effective depth you will do to find out the effective depth. Okay, sorry, to find out the effective length. Then like that actually you have to calculate. So you just go through these clauses, you will understand. For now we will be only requiring the clause E, so that is what we want. So as basically this condition is satisfied, L by means support width is less than L by 12, so we will be using this one. As per that, the clear span plus effective depth, or clear span plus support, half the support width or the center to center support width. Then the effective length is Lx by d by 2, which is 3.46 meter over here, or the width of the support, that is 3.63. So whichever is less, so this is the lesser one, so that will be taken as your effective span. So effective span is 3.46 meters. Okay, so please go through these clauses, and if you do not understand any clause, then let me know. Now we will go for the load calculation. So here it is given that the load are given without the sulfate. So as we have decided the overall depth should be as 160 mm, so we can find out. So the unit weight is 25 kN per meter cube into the depth is 4 kN per meter square. Then dead load is basically unit sulfate plus the floor finish, or the dead load that is given in the question, which is total is 5.5 kN per meter square, and live load is 4 kN per meter square. So now if you do the factor, so 1.5 dead load plus 1.5 live load, so basically the dead load is 8.25 kN per meter square and live load is 6 kN per meter square. These are what? These are factored loads. Now how to calculate the moments, critical moments. So for that, in the IS code, in the table 12, some coefficients are given. You can see here near the, this is for the moment, the bending moment coefficient. Okay, you can also find it in the clause 22.5.1. here it is mentioned a span moment and support moment. See, span moment and support moment. What is span moment and what is support moment? That means if you are talking about the span, that means a negative, here just the sagging moment. Span moment is nothing but the sagging moment, which is represented by positive here, and support moment is the hogging moment. Okay, because near the support itself we'll be having the hogging moment, right? So this is always represented as negative, this is positive, this is negative. Understood? Now it is mentioned here as near the middle end span and at the middle of interior span. Here see, look at these two terms, end span and interior span. Suppose for our problem, this is the total whole slab. Both ends are simply supported over two walls, and in intermediate we have beams. So this is basically the end span. These two are the end spans. Okay, and these are the interior spans. So whenever I see the end span, so we are talking about this, and whenever you're talking about the interior span, you are talking about this. Okay, and other than that, the type of loading, if we're talking about a dead load and imposed load which are fixed, then the moment coefficient is 1 by 12 and is 1 by 16. That means here at the end it is 1 by 12 and it is 1 by 16 over here. It is 1 by 12 over here. Understood? Then if you're talking about the imposed load, in that case, that means live load, it is 1 by 10 over here, 1 by 10 over here. We are talking about only sagging moment, because the span moment we are talking, sagging moment we are talking. Okay, 1 by 10 over here, 1 by 10 over here, and 1 by 12 over here, 1 by 12 over here. Understood? And similarly, if you talk about the support or hogging moment, support moment, at the support next to the end support, at a support next to the end support, that means it is talking about this support here, at a support next to the end support. This is the end support, next to the end support is this one, and this is the end support. So these two supports are they are talking about. Okay, so it is minus 1 by 10 for dead load, here also minus 1 by 10. Probably you cannot see, so here it is minus 1 by 10, minus 1 by 10. Okay, minus because we are talking about hogging moment. Hogging moments are represented as minus, and for live load it is minus 1 by 9, minus 1 by 9. And all the other interior supports, here we have minus 1 by 12 and minus 1 by 9. Understood? But at the end support it is not given. At the end support it is not given. Here you can find that okay, we will see later. So also it is mentioned for fixed shear force, also for shear force calculation, the similarly at the end support and at support near to the end support and all other interior supports. Okay, at the end support these will be the coefficients, and at the interior support these will be the coefficients, and at the support next to the end support these will be the coefficients at the outer side and at the inner side. Outer side means let me show you. Suppose for our problem, this is the case. So for dead load we have at the support is 0.4, that means here will be having 0.4, here will be having 0.4. Then at the support next to the end support, yeah, we are talking about this support right now. We are talking about the support which is next to the end support. So here at the outer side, so this is the outer side, this is the inner side. So outer side we have 0.6 and the inner side will be having 0.55. Here in the outer side we'll be having 0.6, at the inner side we'll be having 0.55, and all the other interior support it is 0.5 and 0.5, because the if you see, the shear force diagram will look like this, something like this, right? So we'll be having outer side and inner side. Outer side, sorry, these are the interior, so this is the outer side, this is the inner side. So that is why these values are given. Okay, so as we are doing for slab design, so shear is not of that much concern, but as when we'll be doing a beam design, then this will be required. Okay. Now let's calculate the moments for the inspan. Suppose for the inspan, that means this span we are talking about, inspan, this span, this span. Okay, these are the end spans, right? And these are the interior spans. Okay. Now for the end span, here mu1 is basically, at first we are calculating the end span I am taking. So let's draw it. Okay, so at the support, where this is the end span here, this is the end span over here. So at the end span, at the support, will be having negative moment, right? It is mentioned that okay, another thing that I should show you. Okay, the what to do with these coefficients. So it is mentioned over here, for obtaining the bending moment, the coefficient shall be multiplied by the total design moment and effective span. Total design moment and the effective span. Okay, the it should be coefficient shall be multiplied by the total design load and the effective span. Understood? Total design load and the effective span. So that is what we will going to do. Okay, so it is mentioned in the clause, that is 22.5.1, 22.5, if the inspan, if it is supported by, suppose some, or it is supported over some walls, in that case partial, you will not find the full moment, because it is just like simple supported, as well as the wall is there. Because of the wall, certain amount of moment of resistance you will find, and that value is basically given by W L square by 24. Okay, you have to remember this WL square by 24, and that is why we have taken is the dead load plus live load by 24. That will give you into L square. Okay, WL square by 24 into 1 meter, because we are talking about, we have taken only 1 meter strip, so that is why multiplied by 1 meter. So mu1 becomes w1 plus w2 by 24 into L square into 1 meter, which is minus 7.108 kilometer meter. So this is somewhere here, minus 7.108. Okay, and at the mid span, it is already, we have discussed that it is for dead load it is 1 by 12, and for imposed load it is 1 by 10. You can see in the table, you will find it. For dead load is 1 by 12, and for live load is 1 by 10. So that is why dead load into, it is mentioned that the coefficient will be multiplied with total load into the length. Total load will be what? Total load in W, this kilometer per meter square, into the area. Area is L effective into 1 meter, right? So into another length it should be there, so that is why L effective square. So don't bother about that, just you remember these equations. If you remember this, or if you try to understand, you will definitely understand. So here dead load by 12 and live load by 10 by into L effective square into 1 meter, so it becomes 15.413. so here the moment is 15.413. then it will go over here and it will go up. So at the up, at the here, means near to the next to the end support, we have minus dl by 10 by 9. Okay, minus is there, live load by 9, dead load by 10, and effective square is minus 17.858. So here it is minus 17.858. Okay, then it will again go down. So it is similar in this side also, because it's also Inspan similar. Then it will come, we are talking about now inner spans, right? So let's see, sorry, let's see the inner span. Yeah, yes. So in the inner span, we'll be having WL by 8, the dead load by 10 plus live load by 9, into L effective square into 1 meter. So that will give us 17.858. Here also it is 17.858. Then at the mid span, we'll be having dead load by 16, live load by 12, L effective square into 1. So we'll be having here, we'll be having 12.159, and again it will come up over here, and this value will be minus 16.212. Okay, this is dead load by 12 plus live load by 9, L effective square into 1. So this is for interior span. So accordingly you have to look for in the table. So as this is symmetric, so it is similar over here also. Okay, so the moments are now available with us. So as the moments are available, we can go for calculating the reinforcement. Okay, now in this particular drawing, it is mentioned at the support it is basically 24, at the mid span it is WL, dead load by 12 plus live load by 10, it's positive value, and at the support it is dead load by 10, live load by 9 into L square. 1 meter is not there because assuming that the width is not considered over here. So, or you can say the loading is in kilonewton per meter over here. In our case it is kilonewton per meter square, so 1 meter we have to multiply. So you can see to this particular figure also to understand, as it is in support. So this is 24, L by 24, and if it is a fixed, then I think you can use this the same equation for the end one also. In support also the same equation you can use. Now calculation of the steel, I think there is nothing much to discuss, and here we have seen that there are different types of moments you can see, but we will now, for ease of our doing, so we'll find out the maximum moment and the minimum moment, maximum hogging moment and minimum hogging moment, maximum sagging and minimum sagging moment. So here hogging moment, if you see, that is maximum hogging moment is 17.85. Each is a 17.85 is the maximum, and 7 is the minimum. And sagging moment, if you talk about, is 15 and 12. So 15 is the maximum one. So let's find out what is the maximum of sagging moment, which is 15, and for that actually we are going to find out the steel, and that comes out to be around, how to find out, I think you know, I no need to repeat. So the spacing is as per the criteria that is required for slab, that is 3D, and here we have got a spacing of 133 mm, and assuming 8 mm bar, a spacing of 110 we can provide at the mid span. So assuming 8 bar, so we can provide 110 mm in the center, and what is provided is around 456 mm square. Okay, and what is required is around 375. So obviously we have provided a larger value, so that is okay. And reinforcement near the interior support, at the near the interior support we have the maximum value as 17.858 from the moment itself. So from the moment you can find out what is the maximum is 17, so you can find out why I have used this mod and all. This is for the purpose of writing the document. That means though it is negative, so minus sign is not needed. So it is the minus sign or the positive sign only represent a direction. So we are only talking about reinforcement over here. The moment value, absolute value you have to take, and the only difference is that for the hugging moment you have to provide the reinforcement at the top, and the sagging moment you have to provide the reinforcement at the bottom. So for maximum 17.85 kN meter, so around if I provide the steel, it is around 438 mm square of steel is required. So if you talk about 8 mm bar, around 114 mm of spacing is required. So let us provide that 8 mm at a 110 mm sample center at the integer support as well. So and near the end support you can see the very smaller amount of moment is there, because of as it's not fixed, and as well as it is only supported over the wall, so a very small amount of moment is there. And that moment, taking care of this moment, we can find out that we can provide it bar at 27%. Okay, and distribution bar I have already discussed with you, that is around 0.12%, and that comes out as around 8 mm bar at 220 250 mm center to center. Okay, this is what we got. So I'm going a bit fast for this section because you already know about all these things. And remember that this question is only for slab. If it is not slab, it's a suppose beam, then the detailing part will be different, just like what we have done in case of designing of beams. How we have done the detailing, the same way you have to do the detailing. So okay, and here we have not gone for checking for shear reinforcement or the shear, because in slab the shear is not that much. So the shear is not that a big issue here, but in case of beams, the shear will be a very huge issue. So you have to find out the shear reinforcement also, and you have to do the shear calculation as per how, as it's a similar way that we have done the moment calculation, the same exact way you have to do, but the only difference is the coefficients values you have to take as per the table. And I hope you can do that, you can do by yourself. Then we have to do the deflection check, and so far the deflection check I have given, or we have only taken care of, or we have taken the particular graph that is given in the IS 456, but there are some tables are also available. This is in Pillar manner. You can take a screenshot of this, or you can take printout or xerox of this. It will be useful for your solving the questions in the exam also. So you can take a printout of this, where different percentage of steel, and what is the FST, and what is the different KT values for different FS values are given mentioned, and it is just for KC values. So here we have to check for deflection. So here AST provided is here is around 456, and actual effective depth is 126 mm. So what is the percentage still provided is 0.326, sorry 362. And what is the FST, which is around 197.765. And for that, exactly 197 is not available with us. 197 is not available, so we can do the interpolation. So assuming that fs is less than 197, that is 190 is available with us, so we can take 190. And percentage of steel, we can iterate. So for percentage of steel, pt is p percentage of steel zero point 0.3, kt1 is 0.189, for fst is 190, and pt is zero point 0.4, it is 162, and we have a percentage of steel of 0.362. So for 0.362 we can find out what is the kt value. And if that value is taken, and here also 20 plus 26 by 2, because of our condition, that is the end is supported over the wall, so it's just like a simple supported, and other is continuous, so we have taken a combination of these two. So it is around 40.452, and what we have provided is 27.46, so definitely it is okay. Now if you look into the detailing, the detailing is very important. You can see here, uh, here we have provided over here a reinforcement which is the length of 0.1 L1. Okay, this is L1, this is L2. The top reinforcements we provided, the whatever reinforcement we will be providing, that should be the up to a length of 0.1 L1, and here it should be 0.15 L2 from the center to the center of the support to this, it is 0.5 L2, means where we will be curtailing the bars. Okay, because some or curtailing or crank, so you can either do crank, just like in one-way slab we have to do, we can do crank or curtail. Okay, so and this distance is basically means way to do the crank, it is 0.15 L1. And here at the support, at the interior support, you can see that if I'm doing the crank, then it is the distance should be greater than 0.15 L1, 0.15 L1 as well, but some other bars should be extended up to that distance of 0.15 AS2, that is basically the reinforcement, this is AS2, and half of the steel that is provided for hogging, that should be given, or that should be provided up to a distance of 0.3 L1, that is half of the AS2. This is for the hogging moment, whatever steel that you have got for hogging moment, that steel means basically up to a length of 0.L51, whatever the spacing that you have provided, it is all along, but half of that steel as an alternate bar should be extended to a distance of 0.3 L. So all the bars will be extended to 0.15 L1, but half of the bar or the alternate bar you have to extend beyond 0.15 L1 to 0.3 L1. Okay, just like here, similarly on the other side also. And here you can see this 0.5 AST2 because AST1 is what is required for the sagging moment, and then it is some bars will be cranked upward, so one bar is at the bottom and the other bar will be cranked upwards. This is an alternate bar concept. So alternate bar, as it will alternate bar will be cranked up or curtailed, so it will be remain with only 50% of what we have provided at the support, that is 0.5 AST1 is mentioned. Okay, so try to understand this of your own. If you do not understand, so you might find it a little bit tough, so you just try to go through this. If you do not understand, please let me know, I will discuss it again. So for our case, you can see the reinforcement we have provided 8 mm bars. These are the main bar, which is 110 center to center over here, 220 center to center, like this. Okay, so with this I would like to conclude today's class. Thank you.